The Zoom session is being brought to you by the fractal almond octaves Z forming. Here's stage 1, stage 2, stage 3, stage 4, whatever. All right, here we go. Today, well, it's the last of the assigned sections. It's where we do connect trigonometry with vectors, with linear algebra, for something called the dot product. This is a way to multiply vectors, but it's a funny kind of multiplication because it takes vectors, you multiply them, and you get out a number. So it's an odd kind of thing. It has two definitions, one geometric, one algebraic, given two vectors, v1, v2, and w1, w2, with their given lengths, length of v, length of w, and an angle theta between them. So the two definitions are v dot w is v1 w1 plus v2 w2. You multiply the corresponding components and add the result. The other definition is length of v times length of w times the cosine of the angle between them. Okay, you can prove various ways that these are the same define the same thing. Okay, various rules. One is that v dot w equals w dot v, so it's commutative. V dot the zero vector is the zero number. Okay. V dot v equals v squared. Now that should make sense because v dot v will be v1 squared plus v2 squared, which is the length squared by Pythagoras. Or here v dot v is length of v times cosine of 1, which again will be the length of v squared. If you multiply v by a constant, by a number, then kv dot w is k times v dot w. So this is a kind of associativity. There's also a kind of distribution. U dot, a sum, v plus w equals u dot v plus u dot w. Also, the I vector in the x direction, unit vector in the x direction, dot itself equals 1. The j vector, unit vector in the y direction, dot itself equals 1. And I dot j equals 0. This follows from cosine of 90 degrees equals 0. Now the angle, from here, we can derive the angle between vectors. You divide by length of w, divide by length of v, and take arc cosine. And the theta, the angle, is arc cosine of the dot product u dot v over the length of u times length of v. Now we call vectors orthogonal if their dot product is 0. That means at right angles. So I and j are at right angles. And again, that makes sense because if cosine of 90 degrees equals 0, so if the angle is 90 degrees, then the dot product is 0. And vice versa. If the dot product is 0, then they're at 90 degrees. So they give some examples. 2i plus j is v, I minus 2j is w, so v is 2 by 1, w is 1 by negative 2. What's their dot product? What's the angle between them? Okay, v dot w is 2 times 1 plus 1 times negative 2. That's 2 minus 2, and that's 0. The angle between them is arc cosine of u over the length product of the lengths, which is arc cosine of 0, is 90 degrees. These are orthogonal vectors. Here we have v is 3 by 4, w is minus 6i minus 8j minus 6 by minus 8. What's their dot product? What's the angle between them? Well, v dot w is 3 times negative 6 plus 4 times negative 8, comes out to negative 18 minus 32, comes out to negative 50. Length of w is root of 3 squared plus 4 squared. That's root 9 plus 16 is root 25 is 5. Length of w is 6 squared or negative 6 squared. Root of 6 squared plus negative 8 squared, which comes up to root of 36 plus 84. Root 100 is 10. So the angle between them is the arc cosine of the dot product or the product of the lengths. That'll be the arc cosine of negative 50 over 5 times 10, which is arc cosine of negative 1. And that is 180 degrees. So these vectors are what are called anti-parallel. They point in opposite directions. And you can see that. You take 3 by 4 and multiply by negative 2, you get negative 6 by negative 8. So they point in opposite directions. Here, find a number a, find a what? Find an a, such that v equals I minus aj and w equals 2i plus that's a 3j, are orthogonal, are at right angles. Okay, If they're orthogonal, then their dot product is 0. So that'll be 1 by negative a dot 2 by 3 is 0. So that's 2 minus 3a is 0. And after transposing and transposing, a is 2/3. Now here's a concept from physics. Work. Work is a measure of energy. It's a form of energy. It's basically a distance displaced dot product of force exerted along the displacement. So if a force F is exerted along a displacement d, then it does work equal F dot d. If F and d are in the same direction, it's just the lengths multiply. And if F and d are at right angles, then the dot product is 0 and the force does no work. So for example, here's a force of 3 pounds at 60 degrees from a displacement from 0 to 6. Force is 3 cos 60 degrees by 3 sine 60, which is 1.5 by 3 root 3 over 2. Displacement is 6 minus 0 by 0 minus 0. That's 6 by 0. So the work is 1.5 by 3 root 3 over 2 dot 6 by 0. 1.5 times 6 is 9. 3 root 3 over 2 times 0 is 0. Sums to 9. 9 foot-pounds, which is incidentally, foot-pounds is a measure of energy. Or here we have my rather crude-looking drawing of I guess a van or something. I realize that I drew it looking like a skate. And this is on a tilted road, tilted at 8 degrees. The total weight of the thing is 5,300 pounds. What is the force along the pavement? And what is the force of the van into the pavement? All right. Well, okay, excuse me. Uh-oh, sneeze coming. Excuse me. Anyhow, when we draw a triangle, a right triangle, 5,300 pounds down, here's a right angle here. A is the force along the pavement, B is the force into the pavement. Here's an angle of 8 degrees. By basic right angle trig, A over 5,300 is 8 degrees, so A equals 5,300 pounds sine of 8 degrees. B over 5,300 pounds is cosine of 8 degrees, so B equals 5,300 pounds times cosine of 8 degrees. And after a very small amount of calculation, the force along the pavement, the force that the brakes must exert, is 737.6 pounds along the pavement and 5,248.4 pounds into the pavement. I bring it to one decimal place because this goes down to no decimal places, and this is, I guess it's a little bit more than necessary, but I'll accept it anyhow. So